Thanks for joining us today. We're going to talk about energy optimization. Try to talk to you a little bit about this. Okay. Hopefully you can see the screen. And so talk a little bit today. KLM introduction, who we are, what we do, a little bit about safety. I think every presentation should start with safety. Introduction to steam savings, energy savings, low-hanging fruit, boilers and heaters, distillation, heat exchangers, compressors and pumps, and a Q&A session. So we've got quite a bit to talk about, and so we'll go ahead and just kick it off. Introduction to KLM. Since 1995, we've been consulting with KLM Technology Group, and it's really my last name without the vowels. So everybody asks me what KLM is. KLM is a leading technical consultancy group providing specialized services and equipment to improve process plant operability, operational efficiency, profitability, and safety. So we have a buffet of core businesses. We do training. We have 75 plus training courses that we offer over the internet, similar to what we're doing today. We have engineering design guidelines, which are how to design almost every piece of equipment in a chemical plant: pumps, compressors, control valves, relief valves. Process studies. We do HAZOPs, engineering support. We sell specialty equipment, random packing, structured packing. We have a magazine called Engineering Practice Magazine. We do unit commissioning, unit benchmarking, evaluation of process units. And we're going to talk a little bit about how to evaluate a process unit from the energy viewpoint today. Practical engineering training. So we have these engineering design guidelines, and if you've searched anything on the web, you've probably found them. And so so I would get all these emails from students and young engineers asking for a discounted price for the engineering design guidelines, since they're fairly expensive because companies buy them. So we set up this association, International Association of Certified Practicing Engineers, where you could buy the guidelines relatively low cost. You also get training and certification. So since 2014, we've been developing this program. And then part of that program, we also publish a magazine called Engineering Practice Magazine. And we're honored. On a good month, we'll have 30,000 people come read the magazine. So we're really happy with that, with our response to the magazine. So that's kind of what we want to do. So let's jump into the presentation. Talk first about safety. Health, safety, and the environment is the number one concern. No project or operation can be classified as sustainable, which is the current buzzword, optimized, or excellent unless it's done safely, healthy, while minimizing the environmental impact. We've made great improvements in the last 50 years because we started from such very, very poor performance, multiple deaths and multiple injuries. All right. So we've made great improvements, not because we're doing good today, but because we've come from such poor performance. We've probably gone from F, failing grade, to maybe an average C grade. We've done well, but there's still great opportunities for improvement. Let's continue to improve health, safety, and the environment. KLM has senior engineers with over 35 years of equipment design, operation, hazard experience to help review your operation, improve your health, safety, environmental performance. Don't think we're doing well. All right. We were just doing so poorly 50 years ago to where we've actually improved, but we're still not doing good. There's still great opportunities to improve in HSE. Introduction to energy savings. More than 50% of all the energy in the world is used in manufacturing and process plants. So half the energy that we use is used in manufacturing and processing plants. The best managed plants reduce energy 3% per year. The average plant loses energy efficiency every year due to lack of maintenance. We're going to talk about some of that today. Okay, so the best managed plants reduce energy 3% a year, An average plant loses energy efficiency every year. The best managed plants reduce energy by replacing the aging equipment with higher efficiency equipment. If an older pump has 80% efficiency, you replace it with a new pump that has 90% efficiency, your energy will go down. All right. If you replace this 80% efficiency pump with a new 80% efficiency pump, you've spent lots of money and your energy is not going to improve. The best managed plants, when they do replace equipment, they replace with higher efficiency equipment. Identify your largest energy users. Know where your energy is being utilized. All right. So go identify, these are the places in the plant where we're using lots of energy. How can we reduce that? Track energy usage per ton of high value product. You want to drive up the amount of high value products produced and at the same time drive down the energy per ton of the high value products. It sounds hard, but it's really not. Okay. So you need to track usage per ton of high value products. Don't track total usage. Track usage per ton of high value product. Here's an example. Okay. And so this is a ethylene plant. And this is energy index. So this is energy per ton of ethylene, of C2, C3s, and C4s. All right. And you can see there's a 10-year stretch here. All right. And so 05, 06, 07, I joined the plant in 08. And we drove the energy down 3 years in a row. All right. We began to look for where we were using energy. We began to look what can we do to reduce the energy. All right. And so the energy actually was higher, and then we significantly reduced the energy. We began to look for some of the things that I'm going to talk about in this presentation. We begin to look for excess air. We begin to look for where were we not optimizing energy, and then we actually drove the energy down over these 3 years. And here's the energy performance. All right. So line 6 is the energy performance. 07, 08, 09, and 010. So from 9 to 10, we drove it down 4%. From 10 to 07, we drove it down 7%. All right. So it's doable. Okay. This is very doable. 7.5 energy reduction is about 4.4 million US dollars for a large energy plant. And I've done this twice in my career. Okay. So one set of plant in Malaysia and one set of plant in Indonesia. It's very doable. If you'll follow some of these guidelines, you can generate a chart that looks like this. Energy is a function of several items. Equipment design. Okay. How your plant's designed, how you're designing your distillation plant, how you're designing your heat exchangers, how you're designing your steam systems. All of these things have a big function in equipment design. Plant reliability. If you're up making products, you're going per ton of energy of high value products is going to be better. If you're always down, having power failures, you're having little outages, your energy per ton is going to be very high. Motor power factors. We'll talk about this. Modern motors can have up to a 90% power factor, which is in motors, power factor is an efficiency number. All right. So I'm in a plant, I'm in an EB styrene plant, and I'm consulting, and we track this energy just like we did there, and it went up every year. And I'm in the meeting and I'm going, hey guys, why is your energy going up every year? Well, in Asia, nobody really talks to you in the meeting. So after the meeting, electrical engineer came up to me and he says, well, what we're doing is every time we buy a motor, we buy a low cost motor, which has like a 70% power factor. Okay. And so that energy, I'm going to show you a picture, that energy produces heat. If you're in the tropics and that energy loss produces heat, the motor doesn't last very long. So you have a, a, a double problem. Number one is the motor doesn't last very long and you lose 10% energy efficiency. Go buy a motor with a large power factor. Pump efficiencies. We're going to talk specifically about pumps quite a bit. Current pump efficiency are approaching 90% due to CFD modeling. Your current pumps probably are 80%. All right. So whenever you are going to replace a pump, go buy the 90% efficiency pump. Lighting, we're going to talk quite a bit about lighting, equipment installation, heat exchangers, distillation, heaters, and boilers. So I'm going to talk about each one of these things coming up. If your energy cost is increasing, you need to put together an energy reduction team. The funny thing is just forming the team normally sees an energy reduction. Amazing what increased focus can accomplish. You need to review some of these things I've talked about. Equipment design, particularly heat exchangers, heaters and boilers, distillation equipment to help you reduce energy, often by just adjusting operating parameters. And we'll talk about some, I call that low-hanging fruit, or just things you can do at very low cost. All right, so let's talk about some of them. Each time you replace an piece of equipment, you should improve the energy efficiency of that piece of equipment. This is how the industry gains 1 to 3% energy improvements per year just by upgrading the equipment. You got an old pump, you got an old motor, you got to replace it anyway. Pay the small delta to get a higher efficiency piece of equipment and gain the energy gains. Right now, the cost of energy is very high, and so it makes a lot of sense to buy the energy. Now, your purchasing guy is going to tell you, I can't pay that delta. And you show him the next 5 years, I'm going to save this much in energy. And it'll push it towards buying the better piece of equipment. You should not replace in kind. You should replace with a higher efficiency piece of equipment. Pumps, motors, distillation equipment, heat exchangers. We're going to talk about heat exchangers quite a bit. Your team should be taught to specify replacement equipment for increased efficiency, often with a small increase, but it has a large return on investment. KLM can come in. We can teach your team how to calculate some of these numbers, how to come up with, you got to go calculate money. You can't do kilowatts. You can't do BTUs. When you're talking to managers, you have to calculate money. Pumps, motors, heat exchangers, distillation equipment are all items that can be replaced with higher efficiency equipment. And you got to go calculate the money. And okay, I want you to spend $5,000 more. But in the next 5 years, we're going to save $50,000. Your manager's going to approve that. All right. Of course, we can assist you in specifying replacement equipment, often with only a small cost increase. So we sell equipment. We have partners that can provide equipment. The minimum you should do is let us review the data sheet. Okay. And then if you want to go buy it, you go buy it on your own. Low-hanging fruit are items that can be done quickly at almost no cost. There are several things that can be done at no cost. Low-hanging fruit does not require a plant shutdown. These are things you can do. All right. We're going to talk about several of these. Boilers and heaters are certain things of distillation you can do. Lighting, insulation, instrumentation, people development. All of these things are areas where you can improve and you don't have to shut the plant down, and it's not large amounts of money. So let's talk about some of this low-hanging fruit. Lighting is low-hanging fruit. With the new LED lighting, equipment lasts much longer with lower cost. LED lights last 15 to 25 times longer than incandescent bulbs. The cost of an incandescent bulb is $18. The cost of 25 bulbs is $25. So actually an LED costs less money. The cost of installing 25 bulbs. Well, I said, well, it's probably cost $25 to install a bulb. Time you go to the warehouse, you write a permit, you get the guy there. Of course, in the US, you can't do it for $25. All right. So In the US, it's probably going to cost you $50 to install a single light bulb in a chemical plant. All right. But I just said $25. The cost of installing these $25 is $625. So your total cost by not going to LEDs is $650. Okay. Oh, it's too expensive to go to LEDs. They're $18. No, that bulb cost $18 plus $25 to install it. The cost of 25 bulbs costs $625. This is a no-brainer. Go do this. If you have 15,000 bulbs per year, you have 15,000 bulbs in your plant, 1,500 bulbs in your plant, that's $37,000 just for the maintenance. Okay? So just on the maintenance and the cost alone, you go to LED lightings. And then LED bulb is 90% more efficient than a standard light bulb. So they're cheaper and they use less energy. So this is, people forget about, oh, LEDs are expensive. They're $18. This incandescent bulb is $1. But you got to multiply it by the number 25 bulbs. You got to install 25 bulbs. So the LED bulb is actually cheaper and it uses less energy. Everywhere I go, I still see LED. I still see fluorescent bulbs. Fluorescent bulbs aren't as bad as incandescent bulbs, but everywhere I go, I still see incandescent lights and I still see fluorescent lights. Go change them out. This is low-hanging fruit. It's low cost. You don't have to shut the plant down. Go fix this. Insulation is low-hanging fruit that many people overlook. With infrared cameras, it's easy to see where you need to improve insulation in your home and in your process plants. Here are some typical pictures. So what happens in your home? The insulation falls. This is inside your wall. The insulation falls down. So you can see the bottom half where the insulation is. The top half has no insulation. It's hotter. And this is pretty common in most houses. So you need to fill up the top half of this wall with insulation. Okay, so that's pretty common in houses. All right. Here's a uncoated steam pipe, 120 degrees. Here's insulated pipe, 50 degrees. This is pretty simple math. You walk around your plant, you got a little camera, and you can easily see where you need insulation. Again, you don't have to shut the plant down. This is low-hanging fruit. It's done a lot of money, but it's going to save you money. But most places I go, they probably need to do this. Okay. And I told you I'd show you a picture of a motor. Here's a picture of a motor. This is a very poor efficiency motor. It's very hot. And so you can obviously see that the motor's hot. It's not going to last very long. And then instead of the power going to move the fluid, you're losing your energy in lost heat. Low-hanging fruit. You don't have to shut the plant down, and you're going to have to replace the motors anyway. And here's an example of a low efficiency motor. And piping. Obviously, I need to insulate this piping. And so this is low cost, and it doesn't require you to shut the plant down. In process plants, most studies show the two largest failure modes are operator error and instrumentation. If I was a plant manager, I'd have a large training budget to reduce the operator error, and I'd have a large instrumentation budget so I could get a bigger yearly bonus. All right. A lot of you are going to be plant managers one day. A lot of you are going to be making decisions about how plants are run. Earlier in the presentation, I said, go look for your largest energy user. Try to work on it. This idea is look at your two largest failure modes and try to reduce them. So the two largest failure modes are typically operator error and instrumentation. All right. So I'd have a large training budget and I'd have an instrumentation budget. Okay. I'm going to get a bigger bonus. I'm going to sleep better at night. I'm going to keep my job as the plant manager. We clearly understand we need to replace our phones every 3 to 5 years to keep it dependable. But for some reason, We think process plant instrumentation should last 20 years. This is not true. Have a budget to replace the electronic instrumentation every 10 years. I think 10 years is too long, but it's definitely not going to last 20 years. All right. So you need two budgets. You need a training budget to reduce operator error. You need an instrumentation budget to replace the electronic instrumentation. These are your two largest failures. All right. So it's very commonly depends on each employee's understanding of the key business components. So reduce your operator error. Let your operators start to understand the principles behind what they're doing. Give your operators the knowledge they need. Of course, KLM has taught 1,500 students all over the world with a wide variety of subjects, and we'll be happy to custom build a training program for your particular team. Boilers and heaters. Most places I go, boilers and heaters are generally operated with high excess air, leading to a loss of efficiency. The best practice is to have about 3% excess air to get complete combustion. If you have too low an excess air, you'll develop CO and you'll get some black smoke out of the furnace. All right, so it's not a good idea to have too low. Too high in excess air, you burn excess gas just to heat the air that goes through the furnace. A lot of places I go, they have greater than 8% excess air. And so they're wasting a lot of energy. Okay. Again, the challenge of boilers and heaters is instrumentation. In my experience, oxygen analyzers are very undependable. Many brands have an O2 sensor that needs to be replaced several times a year. And so I'll walk up to most heaters, they'll be running 3%, exactly what they want them to do. You take an external sample and it's 8% because that sensor has gone bad. An easy way to check the excess air is to have the lab sample weekly. They can catch a sample and the analyzer can be calibrated when needed. For a large heater, excess air can cost more than $10,000 per year. If your plant has 10 heaters, this is $100,000 per year. Okay, just to replace that O2 analyzer. All right, we put way too much trust in instrumentation. Okay, we need we're learning now in LOPAs and HAZOPs that for dependable, I need 3 pressure transmitters. I need 3 instruments. Okay, to be real dependable, you probably need 3 oxygen analyzers, and most have 1 and they don't work very well. So I'm talking to this one company about boilers and heaters, and most of them I walk up to, and the guy tells me, he says, well, our boilers are real good because every time we have a third party come in and test them, we always pass. Yeah, because 2 weeks before that third party comes in, you've calibrated all the instruments, you've worked hard. The other 50 weeks a year, you're probably in trouble. But for that 2 weeks, you've passed. Okay. And so you need to don't necessarily trust your oxygen analyzer. So I asked this one guy, how good's your oxygen analyzer? Oh, we're running 1.5% excess air. I said, well, you're probably not, because if you're running 1.5% excess air, you'd probably have black smoke coming out of your furnace. So don't depend upon these oxygen analyzers. Don't depend upon your 1-year yearly test where you've calibrated all the meters the week before. Go run external test on these O2 oxygen analyzer. Again, this is low-hanging fruit. It's not, you don't have to shut the plant down, and it's not big money. It's $100,000 a year, and it's energy. Okay. Now I keep talking about cost when I talk about energy, because if I talk about kilowatt hours, my manager's not going to care. If I say there's $100,000 on the table here, he's going to go spend the money to get the oxygen analyzers calibrated. We'd be happy to come review your boilers and heaters. We'd be happy to review your systems, hold a training class for your team. Normally, if I'm going to come, I'm going to request you buy a portable oxygen analyzers about this big to cross-check your heaters. All right. We'll walk out there. We'll buy a little portable oxygen analyzer, and we'll check your heaters. Of course, I'm going to request you buy it, and you can use it from then on. But again, they got these little O2 sensors. They last about a month and a half. You're always changing them O2 sensors. So, but here's $100,000 on the table. All right, easy, $100,000 in most plants. Distillation equipment. So we've talked about insulation, we've talked about lighting, we've talked about boilers. So distillation equipment, KLM is recognized as a leader in distillation equipment design, operation, commissioning, troubleshoot. We can provide distillation process studies, distillation engineer operators training. We can do tower inspections, which we're going to talk about, and we can do distillation replacement equipment. Did I go the wrong way? All right. Distillation equipment. The major issues with distillation equipment are incorrect installation. You'd be surprised the number of places. I'm fixing to show you some pictures where the installer installed it wrong. They had a third-party inspector installed it wrong. The tray manufacturer came in and okayed it, and then I came behind them and reviewed it. And I'm going to show you a bunch of pictures where they were done wrong. Operations, okay? Most places I go, they're over refluxing. All right, if you do over reflux, your reboiler is running too high, you're using too much energy. The reason you over reflux is it's real comfortable for the operator to over reflux. High pressures, I go most places, the pressures are too high on the distillation columns. We know if we lower the pressures, it's going to take less energy. All right, so the two things, I can walk in, low-hanging fruit, I don't have to do anything. I can cut the reflux back, I can lower the pressure, I use less energy. Don't have to do anything. Low efficiency equipment. Because we buy low cost, we buy low efficiency. And we don't understand yet the cost of that low efficiency equipment. A standard sieve deck tray is at least 10% lower efficiency than a high efficiency tray. Okay, so I can replace the trays, pick up 10% efficiency. For like a refinery, which is 50% of their energies in distillation, that's 5% energy savings just to replace trays. Oh, but replacing trays are expensive. No, they're really not. What's expensive is the column shell, is the overhead condenser, is the pumps, the compressors, the DCS. Trays are about $1,500 for a 1 meter tray. So trays are not expensive. What's expensive is everything else surrounding the column. But what does the work is the tray. All right. So you can easily replace the tray and pick up energy efficiency. Tower inspections. A large problem in many towers is the internal inspections they're installed incorrectly, leading to a loss of product quality, tower efficiency, higher energy, and run lengths, plant reliability. Many companies do not have the expertise to review the tower installation. KLM, I can provide a senior tire inspector for your turnaround to assist and optimize tire performance. If it's a big turnaround, I'll actually show up. Okay. But so most companies don't have, I hate to say it, even the major companies have made a lot of mistakes in installation. I'm fixing to show you some pictures. All right. So what do we want to look at? We want to look at downcomer clearance. We want to look at this inlet weir. One of these pictures I'm fixing to show you, this inlet weir was incorrectly installed right up next to this downcomer. The liquid couldn't flow out. All right. So I need to look at this clearance here. I need to look at this clearance. I need to look at the levelness on the trays. I need to look at the top width of the downcomer, tray spacing. All of these things are important. If this if this weir is right up next to that downcomer, the liquid can't flow out. That tray's not going to work. All right. And so let me show you some different pictures here. All right. So here's a picture of the reflux piping not installed correctly. All right. So what's supposed to happen is supposed to come in behind this false weir, flow evenly across this tray, and then go evenly down to the next tray. By putting it just out in the middle of this tray, I've disrupted the flow on this tray, and I've disrupted the efficiency of this tray, probably the efficiency of this tray and the efficiency of that tray below it. If I have 30 trays in this column, I've knocked out 2 trays, which is 6%. So just by not installing this feed inlet correctly, I've knocked out 6% of the energy in this column. Okay. I showed this picture to a distillation conference and the crowd laughed. And so this was a major distillation company installed this. And this is my hand. I'm climbing through a column and I'm measuring the downcomer clearance. So I'm in a distillation column, and they didn't have the downcomer clearance correctly. And so I made them all go, made them adjust these so they'll have all the right clearance. And you can see they adjusted them, and this one's supposed to be 20 millimeters. And so they adjusted it out to 20 milliliters. So I'm looking, and I don't like these valves, these movable valves are pushed up right here. So I don't like the way that looks. And a lot of times I'll jump on a tray and just see how stable the tray is. So I don't like these valves sticking up. And I kind of jump on the tray, and I don't like how stable the tray is. So I said, well, let's see how tight these bolts are. This was a major distillation company, and I'm falling behind them. And I reached up to see how tight this bolt was. It came out in my hand. I said, well, let's look at these 2 bolts. And all 3 of them came out in my hand. So I'm looking at them, and I'm going, well, guys, what happened? Well, we needed longer bolts, and it just didn't fit right. So we just stuck them in there. What they don't understand is once you start this column up, this tray is going to lift up, and I'm going to wipe out probably 3 trays. Again, if I've wiped out the tray above it, this tray, and the tray below it, I've wiped out 3 of 30 trays. I've just wiped out 10% of the efficiency on this column, just because I'm too lazy to go get the longer bolts. All right. And they all looked at it. Everybody says it looked good. They don't understand that simple things mean a lot. This is a 10% energy hit right here. Okay. Distillation replacement equipment, trays, packing, stranded packing. So we provide distillation equipment at significantly lower cost than the major distillation companies due to our lower overhead costs. Most major companies have thousands of employees and offices worldwide, leading to a fixed high overhead cost. KLM has limited overhead costs. We pass these cost savings on to your team. All right. So I think we know what we're doing, probably better than many companies, and we have low overhead. So you're going to get a high knowledge base, and you're going to get low cost. So obviously, we think you ought to come to KLM to buy replacement equipment. So here's some pictures of some crude unit trays. Okay, obviously they need to buy stronger trays. I don't like this type of valves. And so I would not choose this type of valve, and I'd probably buy stronger trays. Okay, so these are some typical crude unit trays. I would not replace in kind here. I would buy better trays. Fouling. So here's some random packing. This is called Cascade mini rings. I actually, for heat exchange, I like Cascade mini rings, which look like this. All right. They're stronger, and they're more robust, and so if I'm in a quench tower, I'm going to buy Cascade mini rings. If I'm in most other applications, this is called IMTP. And it is proven it's for its cost, it is one of the higher efficiency. If you look at cost per efficiency, this ring is probably one of the better choices. There's some higher efficiency rings, but they're also very high cost. All right. So for quench towers, for heat exchange, I like Cascade mini rings. For most other, I like IMTP. These are called Paul rings. I don't particularly like Paul rings. They're used in a lot of services. And let's talk about this picture next. So here's an ethylene plant case study. Plant in Malaysia opened up their quench oil tower and found the random packing had disintegrated, causing very high pressure drop and fouling. Why did this happen? So they're supposed to have rings. They don't have any real rings left, and it's full of coke because now since the packing fell apart, it became a filter. All right, so you got very high pressure drop. I've got low run length. How did this happen? What caused this? One cause might be galvanic corrosion. The packing was stainless steel. The tower wall was carbon steel. Always consider galvanic corrosion when you're designing with multiple metallurgies. All right. So what happened? This quench oil tower had acids, had caustics, had water, had all of these multiple things floating around. I had carbon steel walls. I had a stainless steel packing. The packing disintegrated and formed this huge filter, which had very high pressure drop. Opportunity loss was well over $1 million. They had to shut the plant down. They were losing energy every day, and they also had short run lengths. So anytime you're designing something, go think about galvanic corrosion. Now, KLM will provide, a lot of times the vendors don't want to provide carbon steel packing. The original designer had a carbon steel wall and carbon steel packing. When they replaced it with stainless steel packing. All right. So a lot of vendors don't want to supply carbon steel packing. KLM will order you and supply carbon steel packing. Okay. So particularly in quench oil towers for ethylene plants, you need to match metallurgies. Or you're going to get pictures that look like this. Gas processing. This is a picture of fouling in an amine column. This tower was packed with Paul rings. Paul rings have low efficiency and they're not fouling resistant. All right. Amine towers are just going to foul. All right. But let's don't use Paul rings. Paul rings are not very efficient and they're not very fouling efficiency. So, of course, now people's use Paul rings for 50 years. So they're real comfortable with them. But I don't keep repeating something just because some other guy did it when I know it's not working. Okay. So I probably would look at IMTP, which is going to have higher efficiency. They're still going to foul, but at least I'll get higher efficiency. Okay. And so I wouldn't choose a Paul ring. Refining case study. Refinery upgrades the metallurgy in its crude tower top trays to prevent corrosion. So is this the best solution? So in a refinery, if your desalter is not operating very well, in the top of your crude tower, your trays leave due to galvanic corrosion. All right. I have chlorides. I have water. I have all kinds of acids up there, and the top several trays will leave. And so what a lot of people have chosen to do, well, let's put very high metallurgy in the top of this column. Is this the best engineering solution? Well, what happens after several years? The trays stay in, but the wall of the column leaves. And you can go to a lot of towers, and the top 30 meters of that column has had to be replaced. It probably would have been a better idea to let the trays be the sacrificial anode and just replace them every 3 to 5 years instead of this top of this tower. This top of this tower is expensive. Remember, I told you trays was relatively cheap. A tray is going to cost, a 1 meter tray is going to cost $1,500. All right. Now you know pi d, so it's 4 times that. But still, in the big picture, trays are relatively low cost. All right. So if I've got a small column, replace the trays. All right. Don't sacrifice the wall of the column. Sacrifice the trays. Demister pads. It's important to understand the failure cases. All right. One thing we bid on a lot of demister pads, and we do we're low cost. Demister pads are not complex. We're low cost. For example, should a caustic tower have a stainless steel demister pad? We know caustic and stainless steel is not compatible, but most places I go, a caustic tower is going to have a stainless steel demister pad. A polymer composite demister pad would probably be a better idea. Okay. And so you're kind of, again, galvanic corrosion, you're setting yourself up for failure here. So don't set yourself up for failure. All right. If your current system has acceptable run lengths, lower fouling potentials, consider a higher efficiency device. If you replace in kind without a review of the best replacement, you won't be gaining the 1 to 3% energy reductions, increased plant reliability, and product quality. All right. So there's several things in distillation. Correct installation. You got the low-hanging fruit. Run less reflux, run lower pressure, and replace in kind. Don't replace in kind, replace with better. Standard sieve deck, which is the industry standard. A high efficiency tray can see greater than 5 to 10% efficiency gains, as well as 20% capacity gains. And for a refinery, distillation can be as much as 50% of the total plant uses. 1 meter tray cost about $1,500. To upgrade your trays has tremendous return on investment. All right. What costs money in a distillation system is the tower, the foundation, all the piping, the DCS, all this other stuff. Trays are relatively cheap, and trays do the work. So go replace the relatively cheap part and pick up a large energy advantage. If you replace in kind without a review of the best replacement, you'll not be gaining energy reductions, increased plant reliability, and product quality. Heat exchangers. Typical heat exchangers are designed very basic with limited optimization. Again, we buy the very lowest cost heat exchanger we can. Guess what? We're not going to get an optimized model. All right. If you're going to replace a heat exchanger, you should not replace in kind. There are several things that should be done to heat exchangers. If you have a fouling service, which most of you do, your heat exchanger should be designed to be fouling resistant and improve heat exchange as well as reliability. I go into an ethylene plant. These are the pictures I'm going to find in heat exchangers. Okay. So let's look at this picture right here. The bottom 30% of this heat exchanger is filled with trash, coke, fouling materials. So 30% of this heat exchanger has zero heat exchange. This heat exchanger, at least 10 to 15% of this is blocked. So you won't have any heat exchange. These are all, when we do this everywhere I go, I can people can pull pictures that look like this in refineries, in ethylene plants, in all kinds of plants. We can find heat exchangers that look like this, hydrotreaters, any number. All right. Your heat exchanger should be designed to improve heat exchange as well as reliability to reduce fouling. An improved design can increase heat exchange 10% or more with only a very small cost impact, leading to a high return on investment. If every time you buy a heat exchanger, if you Replacing kind without a review of your best replacements, you'll not be gaining energy reductions, increase plant reliability and quality. I have a question here. Let's see what the questions. Uh, please share your presentation for further. Okay, so what we're going to do is I can send you a copy of this presentation, and if you send me an email, or when it's finished, I'm recording this, and I'm going to post this presentation on YouTube. I have a YouTube channel, Carl Coleman's. If you search Carl Coleman's on YouTube, you'll see I've got a whole group of presentations like this. So if you want to send me an email, I can send you this presentation. Probably tomorrow or the next day, I'll actually have it posted on my YouTube channel, this whole video. Your heat exchanger should be designed to improve design, can increase heat exchange 10% or more. Don't replace in kind. If you have pictures that look like this, if your pictures look like this, don't replace in kind. All right, go fix this problem. All right, so how do you fix this problem? Well, the baffles here are supposed to do two things. Number one, it routes the flow. And number two, it secures the tubes in place. But if I have a fouling service, all that fouling material is going to build up and block this bottom half of the tray. Now, remember, this is a circle. So even though it's only 20% blocked, it's probably 40% of the area, right? Okay, so remember, just it's not, this is not linear because it's a circle. So this, if I block these bottom two rows, it's probably 40% of the area, all right? And all of these rows are going to be blocked, all right? So what you ought to do, if you have a fouling service, you notch this baffle so this trash will move this way. The other thing you want to do is you want to, if you know it's fouling service, you want to put it in the top and take it out the bottom, all right, to move it, all right? So there's several things you can do. These are low cost, but nobody really does this. This is low cost. So there's all kinds of baffles. Right here, I'm going to fill this area up with trash. Right here, I'm going to fill this area up with trash. If I put small notches under here, the trash will move. It'll be slightly less efficient than with no notches, but it's going to be way more efficient than if I fill up this bottom section with trash. Okay. So you're going to take a small energy debit when it's clean, but you're going to keep your energy much higher over the life of the run. Okay, so that's what you want to do. You don't want to design these baffles to have trash. Okay, and I just told you I want it to come down, and here's one that goes up. All right, so this one's going up. This whole area right here is going to fill with trash. This whole area right here is going to fill with trash. This whole area right here is going to fill with trash. Okay. So you need to think about how these baffles are laid out. You need to think about which direction it flows. You need to think about how to design this better. These are typically designed. Everybody, okay, they're imagining it's clean service forever, and they're imagining I've got kerosene. Okay, I've got clean kerosene and it's not going to foul. Guess what? That's not the real world. The real world is it's fouling material, and in the real world of that's what my pictures look like. So I found this preheater train, and now my heater's got to do 20% more work to heat my crude, to do whatever I'm doing. So it's very important that we design these heat exchangers correctly. All right. And a good plant will come in. You can do a study. You can determine which are the bad actors, and you can determine which ones you need to change out. Now, this is not low-hanging fruit, but again, we're talking 20% energy loss. We're talking real big money here. All right. And so this is something you need to do a heat exchanger study. You need to pick your bad actors and probably replace some of your heat exchangers. If you got pictures that look like this, which most plants do, you're losing lots of money. You're losing lots of energy. Heat exchanger design. A process engineer designs for 120% of flow. A mechanical engineer comes behind you, designs 20% safety. So we have 140 to 140% of flow. If you're running 80% of design, you may be in laminar flow regime. So what happens if we're in laminar flow? Well, if we're in laminar flow in a heat exchanger, we have a significant loss of heat exchange. All right. We're in trouble. Can you still hear me? Somebody raise your hand if you can still hear me. Can you still hear me? Somebody raise your hand if you can still hear me. Okay, good. Thanks. My microphone fell off the table. The microphone thing fell off the table. I was worried you couldn't hear me. Thanks. Okay. You are audible. Okay, good. All right. I worried about it because there's got a little microphone adjustment and it kind of fell off the table. So I'm going, well, did I lose my people? Okay, thanks. Okay, so how do I close this? Okay. All right, so what happens if I run into laminar flow? So if I run into laminar flow, I get a layer of really not moving liquid along the pipe wall of this heat exchanger. If I'm in turbulent flow, the liquid flows. All right. So if I design for 140% and I'm running 80%, I may be in laminar flow. If I'm running into laminar flow, there is a significant reduction in heat exchange. All right. And so I need to look. I need to do a study. I need to do a Reynolds number study. Am I in laminar flow? Am I in turbulent flow? If I'm in laminar flow, an easy way to do is plug some of the tubes. All right, I've done that before. I've gone in and plugged 5% of the tubes. I brought it up to turbulent flow. I picked up 15% energy change. Another way is add inserts. Inserts are things you put inside the tubes. Some inserts are better than others. Some of the inserts I don't like. They've had a lot of failures. Other inserts have worked real well. So you need to perform a study on your heat exchangers. You need to determine which ones are fouling and to redesign them. Sometimes it's easy to redesign them. Just notch some of the tubes, notch some of the baffles. If you're in laminar flow, you probably need to plug some tubes. All right. All right. And so these are easy things to do, can significantly improve your heat exchange. If you've got pictures that look like this, if you've got if you're running into laminar flow, there's things you can do simple things you can do to increase your heat exchange. Sometimes you're just going to need to replace the heat exchanger. Okay. But again, this is a lot of money. If you're not getting the heat exchange, you're running high duty in your heater, and this is a lot of money. All right. We have a senior team to specify and supply your heat exchangers. Because we build a lot of heat exchangers, we can provide a higher efficiency, better designed heat exchanger at the same cost that you're currently purchasing. The minimum you should do is have KLM review your designs. Pay us to review your designs. Then go take that design and you can buy it. You can buy it. But I really think we can supply them cheaper than you probably can buy them. Pumps. Current pump designs have higher efficiencies due to safety modeling. If you're going to replace a pump, consider increasing the efficiency of the pump. There will be a small cost impact, but it has a huge return on investment. If you're buying an 80% efficiency pump, you replace it with a 90% efficiency pump, you're picking up 10% energy savings every time you do that. All right. And that's how the major companies are getting 1 to 3% energy savings per year. They're doing some of these simple things. Because we buy lots of pumps, KLM, we can provide a higher efficiency pumps, probably the same cost as you're currently purchasing. A lot of plants only buy 1 or 2 pumps a year. The vendor is knows you're only buying 1 or 2 pumps a year and you don't get discounts. KLM and our partners are probably buying 50 to 100 pumps a year. And so we get discounts. All right. And because we have low overhead, we can pass that some of the cost savings on to you. Introduction. KLM has several ways to support your team: process studies, safety, reliability, quality, and cost, training for your team, specialized equipment replacements. These are things that we can assist your team with. Process studies. Number of process studies, a wide variety of processing plants, refineries, ethylene plants, natural gas. We can bring this large database of knowledge to assist your team. Training for your team. Obviously, you've seen some of the training similar to what we're doing today, and we've taught over 1,500 students all over the world. We'd be happy to come in and teach your team. Specialized equipment, distillation equipment, heat exchangers and pumps. These are all things that KLM can provide. What projects have we done? So here's a project that we've done. Here's a pump skid that we put together. This is this 3D model of the pump skid. There's the actual pump skid that's built. So we bought the motors, we bought the pumps. These are the seals. And then here's another skid where we bought the heat exchangers and the overhead condensers. Here's another. So we do quality work. You can see this is very high quality. We build small skids. There's a clay treater. It's filled with clay, and you treat kerosene, or you can treat other things. You can treat mixed xylenes in clay treaters. There's quite a few things you can treat in a clay treater. Here's the actual built clay treater. Distillation system. You saw the skids already from the distillation system. You saw the pumps already from the distillation system. So we build a lot of pumps. We build a lot of skid packages. Here's the 2 distillation columns. And so we have over 20 distillation products. We build over 40 heat exchangers, 25 pumps, over 20 pressure vessels. So because we're volume, we can buy low cost. And because we have low overhead, we can pass that cost on to you. For a small job, you probably should come to KLM. For a large job, you probably should go to someone else. Solid track record of projects since 1995, strength in process engineering, strong partners in mechanical engineering, modular fabrication, wide range of industry served. And so what have we talked about today? KLM introduction, some safety, introduction to energy savings, drive it down over time, low hanging fruit, things I can do without a shutdown, boilers and heaters. Okay. Don't depend upon your instrumentation unless you got 3 of them. All right. That's what we learned out of Lopez. Distillation. Installation is a problem. Everywhere I go, they don't install things correctly, and you get a 3 to 5 to 10% hit. We buy low cost trays, and then we have energy heat exchangers. Go look at your own pictures. If your pictures look like that, you need to do something. Pumps and compressors and motors. The newer CFDs, the newer models are 10% more efficient. Go buy the 10% more efficient. So you can easily, with what I've told you today, you can easily do 3 to 10% energy savings. Okay, with these guidelines, it's 3 to 10% is easy. There's all kind of there's all kind of things out there that can help you. If you got any questions, you can mention them now. We're going to put this. If you want a copy of this presentation, you can email me. If you want to, I'm recording it, and I'll probably put it up on my YouTube channel, Carl Comet's YouTube channel, and then so thanks for your time today, and so so we've talked KLM introduction, we've talked about safety, where we're doing good but not good enough. Keep trying. Track your energy. Go look for low-hanging fruits. Don't trust your instrumentation. Distillation. There's a wide range of things. Heat exchanger pictures were really poor, and compressors and pumps. And thanks for your time.